Hello, 8th graders. We are going to continue our conversation about the conservation of momentum in today's lesson. In the last lesson, we talked about the concept, and now we're going to go into the actual numbers of how to do conservation of momentum problems. Like always, you're going to need your notebook for this. Please make sure that you are on a fresh, clean notes page. Make sure that you put a title on there that says Part 2, Conservation of Momentum Calculations, so that you can find your work later when you need it for the assessment. To show you the objectives again, from last lesson we crossed off the first part of this. At this point, if you have finished the last one, you are able to explain the law of conservation of momentum, and now it is time to apply it to a situation and calculate. But they're the same concept, the same idea is going to be taking place. It's all about Newton's third law. So the warm-up is on your screen. I need you to go to your practice side and complete the warm-up over on that side. On the screen is today's warm-up. I need you to go over to the practice side of your notebook and answer the 4 questions that are on your screen about a bug hitting a car's windshield. Pause this video and try those questions now. If you are still watching, you've finished the warm-up questions, let's go over them really quickly. So, when that car smashes into the bug, there's going to be a force applied on either one. Well, hopefully you remember from Newton's third law that equal forces happen in both directions. So if the car is going to push on the fly with 10 newtons, well then the fly is also going to push on the car with 10 newtons. And sometimes that's really hard for people to believe because they're like, yeah, but a car just obliterates the fly. And the fly hardly does any damage, or none at all really, to the car. Well, think about like smacking a bug on your arm. Do you really have to hit a bug very hard in order to smush a bug? Neither does a taxi cab. So when those two things run into each other, it's the same exact force being put on both things. It's just that a bug can't take that much force before it's destroyed. You could smack a windshield with your hand pretty hard and it wouldn't do any damage to the windshield. They're the same forces going both directions. So then question number 2, which one has a bigger change in momentum? So the bug is definitely going to stop going this way and go with the taxi cab after it's been mushed onto the windshield. But think about the taxi cab. If some little tiny object is crashing into it, technically won't the taxi cab be slowing down or losing a little bit of its momentum? And the answer is yes, and they're both equal. And if that one's hard for you to get your head around too, it's probably for the same reasons as the last one. A little bug does not have that much momentum because it has so little mass. So it doesn't take very much to change its direction and move it the other way. A big car, on the other hand, has a lot more mass compared to the bug. So when the bug crashes into it, because it is so big, it's not going to change its velocity very much. But technically, it will a little tiny bit. Number 3, which one has a bigger change in velocity? Well, we've already said that one, but the bug, for sure. So if the bug was flying this way at 2 meters per second and then it crashes into the taxi, it's going to change its direction and probably its velocity too, in a whole big amount going the other way, whereas the taxi cab, it might go down just a teeny tiny little bit, but velocity is not part of Newton's third law. Newton said that there's equal and opposite momentums, there's equal and opposite forces, that momentum has to be conserved, but he didn't say that velocity has to be the same. Velocity is a different story. Number 4, how would things be different if the bug were the same size as the car? So imagine you had a car-sized bug crashing into a car, and if they were both going in the same velocity, well, there would still be equal forces, because equal and opposite forces. Momentum would still be equal too. The thing, though, that would be different from what we've already said is that the two objects would have a similar change in velocity this way. So if you had 2 identical objects crashing into each other at the identical speed, the same change in velocity would happen in that case. So today we're going to do calculations, and I wanted to bring up an example of why knowing how to do these calculations is really important to a particular group of people, and that would be NASA. So I want you to think about the International Space Station, which is on your screen, and when they used to use the Space Shuttle, which they don't anymore, but when they used to use the Space Shuttle to bring supplies and crew and all the things that needed to go up to the space station, when those two things would get near each other, we're talking a lot of mass moving pretty quickly. So both of these objects have a lot of momentum. And what they had to do was basically they had to crash with each other. Now, when I say crash, I mean physics word crash, like any two objects that are making contact with each other, that would be a crash in physics. But the scientists had to figure out how much momentum is going from one thing into the other so that they could build all of the parts to absorb that momentum and deal with it so it didn't rip all the pieces up. So I wanted to show you some numbers. Remember, momentum is mass times velocity, so we can pretty quickly find the momentum of objects with just those two things. I looked it up, and the mass of an empty shuttle was 2 million kilograms. Pretty big. And the docking speed, let's just say that it was 0.01 meters per second. So 0.01 is 10 centimeters. That's about like this, maybe the length of my pointer finger, every second. So they're going pretty dang slow relative to like each other, at least. They're zipping around the Earth at a much greater speed, but relative to each other, they're moving about 10 centimeters per second as they move closer to each other. So if you calculate that out, that's 20,000 kilogram meters per second. Just to put that into perspective, that's the same as a small car going 400 miles per hour. Remember, momentum is how much stopping power it needs. So if you want to stop that shuttle as it's coming into the space station, it's the same amount of stopping power as a small car going 400 miles per hour. That's a lot to deal with, so the engineers had to figure out how to deal with that with like springs and compressions and different materials, and it was a big deal to figure out how to make those two things work. Now we're going to get into the actual calculations. I need you to be over on your note side, and if you are a very clean, careful note taker, you just keep doing what you've always done. If you're more on the loose side of things and you just kind of scribble a few things here and there, I really, really strongly encourage you to take your time with this slide as we go through this practice equation, because if you take your time and you're careful about making sure that it looks nice and that it's understandable, when you need to come back and remind yourself how to do the process that we're about to go over, it will serve you well to have a clean notes page. So, first thing on your notes page is we need the equation for momentum. I know it's probably in your notebook, hopefully, from the last time we did this way back in Unit 1, but let's make sure it's there again. Momentum is mass times velocity. And as we talked about yesterday, we learned that all the momentum before a collision has to be equal to all of the momentum after a collision. We're going to take these two things that are in green, and we're going to use them to figure out some missing information, some useful things about collisions. So let's take an example. Let's say that we simply have this blue car that crashes into the red car. And we're going to say the blue car was driving along, and when it crashed, it gave up all of its momentum into the red car. Kind of like when you saw the softball and the golf ball. When they crashed into the floor, the softball gave all of its momentum to the golf ball. Same idea. Momentum is moving into the red car. And we want to figure out how fast is that red car going to be going after the crash. The other pieces of information that we're going to use are that the blue car has a mass of 1,500 kilograms and that before the crash it was going 15. On the other side, we only know the mass of the red car. And that it was at rest, so we know those two pieces of information. So I need you to pause this, make sure that you have everything that's on my screen so far. I also recommend that you use colors if it helps you to keep track. I use colors because we're using the red car and the blue car as we're going to go through. If you're still watching, you're ready to move to the next step. So we need a way to organize all of our math. There are probably a lot of ways that you could do this, but I have found over the years that a table helps me, and so that's how I'm going to show you. So we need to set up a table that looks like this on your paper. It's a table that has a place for us to record the momentum before the crash for both objects, the blue and the red. We're going to do that in these yellow boxes. We also have a place to record the momentum after the crash, again for both objects. And then we can use this green statement. And whatever we find on the before side, we can set it equal to everything on the after side. And we can use Newton's third law to find missing pieces of information. Let me show you how this works. So we just start filling it in using momentum. So we're going to start with the blue car. We want to find the momentum before the crash for the blue car. So we need its mass and we need its velocity, since momentum is mass times velocity. So in that box, we're going to go momentum equals mass times velocity, and we're going to plug in the things we know about the blue car. We pulled from the information above that it has a mass of 1,500 and that its velocity was 15. Calculate those out. We know that the momentum of the blue car before the crash was 22,500. Now let's go to the red car. Since the red car was at rest, we know that the red car had no momentum beforehand. So its mass times 0 is still 0. So now Newton said all the momentum before a crash is equal to all the momentum after. That means we have to combine all the momentum before. So the blue car plus the red car, we add them together, and we're going to drop that number down into the total box. So 22,500 from the blue, 0 from the red, gives us 22,500. Now is a good moment to pause if you need to catch up with your notes. Now let's go over to the after side. So in 8th grade physics, we're going to assume that no objects are going to change their mass. So even though in real life, when cars crash into each other, pieces break off and go flying and the masses change, we're going to ignore that for 8th grade and keep things simple. So if the mass before was 1,500, the mass after is going to be 1,500 also. So to find the momentum after, we do mass times velocity. So in this example, it said that the blue car gave up all its momentum. That means that it stopped. Its motion was transferred into the red car and it came to a stop. So now the blue car has no momentum after the crash. It gave it all up. It's going to go into the red car. So we go to the red car and we know that the momentum has to be mass times velocity, but remember, we don't know the velocity. So the mass is still 1,800, and we're going to use v and just leave it as a variable in order to find this velocity. So we have 1,800 times v, because we don't know the red car's velocity yet. But all the steps are the same. Now we have to combine the after by going 0 plus this 1,800 v, and then drop it down into the total box below. So that's just 1,800 v. Now comes the part where we combine these two things we've just done. Newton said all the stuff before has to equal all the stuff after, so we're going to just put an equal sign between the two, and now we have an algebra expression. 22,500 equals 1,800 v, and we're solving for v. So since 1,800 is times v, in order to undo that, we have to divide both sides by 1,800, and we figure out that the velocity of the red car after the crash was 12.5 meters per second. Pause this video if you need to add any of these details before moving on. Now I want you to try one yourself. So the setup and the steps are exactly the same. Over on your practice side, I need to see the exact same table set up with the before and the after and the total, and I need you to plug in all of the information. So in this question, I have a mass of 105, and I'm going to be playing hand judo with Timmy. So right as I'm about to shove Timmy, my velocity is 1.5 meters per second. So I'm coming at him at 1.5. I push Timmy, who was not moving. He was just standing there, poor Timmy. He has a mass of 65. After I shove him, I didn't lose all my momentum though. After I shove him, I'm still moving a little bit, so 20.25 meters per second. But I want to know, how fast is Timmy going? If I transfer a good chunk of my momentum into Timmy, how fast is he going to go flying? Pause this video and try it on your practice side now. All right, we're about to check your answers. What you can do is you can grab the slider and you can scrub the video to the end to see if you got the right number. If you got the right number, you don't have to go back and watch me talk about all the steps. If, however, you were a little bit lost or you got the wrong number, then you do need to scrub back and watch all the steps. So let's go through it. So I've got my table all set up. I'm going to start with my before momentum, is my mass times my velocity. So I was 105 kilograms, and I was moving at 1.5, which gives me 157.5. Now I'm going to do the same thing for Timmy's momentum. Since Timmy was just standing there minding his own business, his momentum is 0. He wasn't moving. When I combine those things and drop it below, I get 157.5 for all the momentum before the collision. Now we go to after. It said in the question that my speed was still 0.25 after I shoved Timmy. So I still had a little momentum. And it turns out it was 26.25, so it went down quite a bit. And all that momentum went into Timmy. And it has to be equal to his mass times his velocity, which is 65v, mass times his velocity, but we don't know v. But we're still going to combine these two terms, so 26.25 plus 65v Remember, since this has a v on it, we can't add these numbers together. They're not like terms. So we drop that down into the bottom as 26.25 plus 65v. Now we can set the before side equal to the after side, and now we have another algebra expression. We have to get rid of the addition part first, so in order to undo addition, we have to do some subtraction. So we're going to minus 26.25, my gosh, from both sides, and we get this expression. Once we've done that, now we have to undo the 65 times v by dividing. When we divide, we get 2.02 meters per second for Timmy's velocity. Let's move into a little bit more challenging one. So let's talk about how momentum and velocity have direction. So if you remember, momentum and velocity are vectors. They can go one way and be positive, and they can go the other way and be negative. So let's go back to the fly hitting the taxi cab question from your warm-up. Let's say that the taxi cab was 1,000 kilograms and it was traveling at 15 meters per second going this way. And let's say that the bug was really tiny, 0.001 kilograms, and it was traveling at 15 meters per second also, but it was going towards the taxi cab, so they're traveling towards each other. So in this kind of a question, we need to be really careful about our signs, positives and negatives, because momentum and velocity can have a direction. They could be positive or negative, but mass will never have a negative. You can't have negative mass. It's not a vector. What we're going to figure out is how fast will the two be going together. So the bug's going to smack into the taxi, and then they're going to move along together. How fast will they be moving together after the bug splats on the windshield? What I need for you to do is pause this video and answer these 3 questions before we move on. Since we're doing another practice question, maybe make a line in your notebook, make a little sketch of the taxi cab and the bug so that you remember what this question was about, and then before we actually do the question, I need you to answer these 3. What does the bug have a lot or a little momentum compared to the car? Which direction will the two move after the crash? And what's going to happen to the momentum of the car? Is it going to go up, down, a lot, a little? Answer those now. Ready, go. All right, let's kind of review. So this is kind of going back to your warm-up a little bit. So the bug, I hope you can agree, has a really tiny amount of momentum. Even though they're moving at the same velocity, since the bug is so small in its mass, very little momentum. So when it crashes into the car's momentum is going to overwhelm the bug's momentum. They're going to smack into each other, and they're going to keep moving in the direction of the car. And then at the last one, what's going to happen to the momentum of the car? Well, the bug's momentum isn't 0. It technically has a little. So when they crash into each other, the bug's momentum is going to take away a tiny little bit from the car. So we should expect the car's momentum to go down just a tiny bit. Now we're going to actually calculate. If you are feeling comfortable with this whole process already of finding these variables, you can scroll right to the end and check your answer, kind of like you did for that last question. If you're still not feeling quite confident yet, that's okay. You can work through it with me now as we go together. So let's remind ourselves of the equation and the idea that all the momentum before and after has to be equal. What we're going to figure out is how fast are the two going together after the bug splats on the windshield. So we're going to be solving for a velocity in this part. The information they gave us is on your screen. We know the mass and the velocity for the car. We know the mass and the velocity for the bug. All of these pieces of information are just before. We don't know the velocity after. That's what we're solving for. So we set up our table, just like all the other ones. We've got our car and we've got our bug before and after. In the before box for the car, we put in our mass and our velocity, and the car has a momentum of 15,000. Now here comes the tricky part. The bug is going in the opposite direction, so its velocity has to have the opposite sign. Its mass is still positive though, so 0.001, but its velocity is a negative 15. So that means that its momentum is also negative, because a positive times a negative equals a negative. So the car has a momentum that's positive, the bug has a momentum that's negative. When we combine those two momentums together and drop it down into the box below, we're going to get a number that's really, really close to 15,000 because the bug's momentum was so tiny. But that's all the momentum before the crash. Now we go to after. Neither of these objects have lost any mass, but we don't know how fast they're going. So we're going to use v. So the car is 1000 v, and the bug is 0.001 v. They both get the same variable because they're both moving together. It's the same number. Whatever that velocity is, it's going to be the same number because they're moving together. So we can use the same v. And we add those two things together because it's all the momentum combined after the crash. We drop it down below and we get 1000.001 v. Set them equal to each other. Now we have to divide to get rid of this multiplication problem. And when we do that, we find out that the velocity of the two things is just a teeny tiny little bit below 15, which is what the car was at when it was going. And hopefully that makes sense. When a car crashes into a bug, its velocity is hardly going to change at all because the bug is so little. So then the last kind of question that we need to go over is, well, what if we don't know a mass? So far we've been doing problems where we've been solving for the velocity, and when we're solving for a mass, it can be a little bit different, a little tricky. So let's use this idea as our practice question. And it's, what is the mass of a bat? We're going to have a bat hitting a ball. This is the third question that I need you to have over on your note side. So draw a line, maybe make a little sketch of a bat and a ball so that you remember what this question was about. And we're going to do the third one over on your note side. The information that we're going to have from this one is the velocity of the bat before and after the impact. And we're going to have all the information about the ball. We know its mass. We know that it was sitting on a tee, so it was just at rest before it got hit. And it flew off of the tee at 8 meters per second. So we know everything about the ball. We know some of the velocities for the bat, but we're trying to find the mass of the bat. But our process is still the same. We're going to use our table and just start plugging in the things that we know. So for the momentum before for the bat, since we don't know the mass, we're going to leave it as an m. Our velocity before, it said in the question that it was going 4. So we're going to solve as 4m, 4 times m. For the ball, it was at rest, sitting on a tee. So anything at rest has no momentum, so that's 0. We're going to add them together and drop it down into the box below. So 4m plus 0 is just 4m. Now let's go over to the after side. It's still the same bat, so we still don't know the mass. We're going to leave it as an m. And it's the same m as the before because the bat didn't change. It's the same bat. But this time it said that the bat slowed down. And after the hit, it was 1.5 meters per second. So we have 1.5 times m for the after part. For the ball, it's still the same ball, so 0.25 for the mass, but this time the ball is going really quick because it got hit. It's going 8 meters per second, and I took that right here from the question. We multiply them together, it looks like the momentum of the ball was 2. So we add them together, 1.5 m plus 2, and we drop it down below. Remember, we cannot add these numbers together because they are not like terms. Only one of them has the m. Now we set them equal to each other. And now we have to do the next step, which is combining like terms. Since we have m's on both sides of our equations, we need to get them together. And since there's more on the left, I want to take away the m's from the right. So I'm going to subtract 1.5 m's from both sides to move the m over. And I get this expression, 2.5 m's equals 2. Now I just have to divide by 2.5 so that I can undo this multiplication. And when I do that, I get 1.25 kilograms. So now we found the mass of the bat. In Google Classroom, there's a Google Slides presentation that has 4 different practice questions where you need to fill in the answers. Here's what it looks like. On the very first slide, you're going to have your equation, just in case you need a reminder. And then each of the 4 slides look very similar. And you're going to work through the same process that we've just been doing in these practice questions. In order to type into these boxes, you will need to grab a text box that's up on the top here, and then start filling it in and resize them to fit the different boxes. If while you're working you need a hint, in each one of the slides there's a text box that's covering the hint. All you have to do is delete the blue box and you can see the hint. And then there's also the answer video. You can click on this to go to the link to see how I solved it. I need you to try all 4 stations before you come back. Pause this video and go do that now. If you are still watching, you've tried all four of the practice questions in the Google Slides. If you're feeling like you still need some more practice problems, I left a link for some Khan Academy practice questions. They don't set up their questions in exactly the same table that I do. They might solve theirs a little bit differently, but they still give good questions and they show the answers too if you need to try more practice questions. For your closure today, there is a Google form for your closure. It's one question about a woman kicking a field goal. I need you to work out the problem on paper before you start punching your answers into that Google form. Go do that now.